So in the last lecture we talked about cubic lattice systems. So we saw various 2D and 3D cubic lattice systems and lattice systems, and in cubic lattice system we have three types of cubic lattice system. One is simple or primitive, one is body centered, another is face centered. So as we discussed earlier, what do you mean by simple? In simple cubic system, all the atoms are at the corners. Okay. In the face centered, all the atoms are at the corners, plus there are atoms that are on the faces. Okay, so let me draw a diagram to make you understand. So okay, the face centered, what happens in face centered is you have atoms at the corners like the simple lattice. Okay, but there is a small catch. So let me draw the atoms at the corners. So these are the atoms that are, so there are 8 atoms at the corners as usual. Okay, now the catch is there are atoms on the faces of each side. So this is a side, so there is an atom here. This is the top side, there is an atom here. This is the bottom side, there is an atom here. This is the side, there is an atom here. The back, there is an atom here, and the front, there is an atom here. So how many face atoms total? 6 face atoms. And how many cubic and how many atoms at the corners? There are 8. So there are 6 face atoms and there are 8 corner atoms. Okay, so this is what we meant by the face centered, as we discussed earlier. So what happens at the body centered? And the body centered, we have only an atom at the center and the atoms at the corners. For example, if you look at this example, you see there are atoms at the corners as usual. There are 8 atoms at the corners and there will be an atom at the center. Okay, so now we'll calculate various things like atomic radius, number of atoms per unit cell, packing fraction. These are the 3 things that we need to calculate for each of these atoms as per the syllabus. So let us start with cubic lattice and we'll discuss atomic radius. So this is a cubic lattice and let us try to understand atomic radius. You see, don't be fooled by this diagram. Okay, don't be fooled by this diagram. Why I'm saying it? Because you see the atoms that occupy the places at the corners, they are not small atoms. And this is not that empty. You see, this is very much empty. This is not the case. This is a false representation. This is just to make you understand, but the truth is they are packed. So this atom is actually not this small, but it can be as big as this, and this atom can be as big as this. Okay, now so this is an atom, this is an atom. So what is the distance between these two atoms? You can easily see that the distance between these two atoms is a, since this is a cubic lattice. Now what happens if I half this distance? If I half the distance a, then I see that I get the radius of each atom. So a by 2 is the radius of each atom. So what is the atomic radius in case of simple cubic? The atomic radius is a by 2. Agreed. But this is not the case when we consider the face centered lattice. Check out the diagram of face centered lattice here. Okay, now I'll draw the diagram again here to give you an idea is what actually is happening. Okay, now what happened in a face centered? You saw that there was atom at the corner and there was atom at the faces of each side. Agreed? Now these atoms are not this small. Okay, so let me flat it and draw what is actually happening. So let me make this side look like this. Okay, and then let me tell you what is happening. You see This atom at the center is actually a big one. Okay, the atom at the center is a big one, and the atom as a corner is also a big atom at the corner. Now if you join this center to that center, you actually get the atomic radius. If you join these two, you get the distance between the two nearest neighboring atoms, and half of this distance is the atomic radius. For example, if you look at this, then this is actually this much big, and this is actually this much big. Agreed? Now, so what is the distance between them? Let me draw a yellow line. So distance between the nearest neighboring is this. So from this point to this point. Okay, and then half of this distance is the atomic radius. So this part is the atomic radius. So let us make the calculation. So let me consider one side and let us do the calculation. So what was on the side? You had this part. Okay, you see in the face centered, the two nearest neighboring are actually the face, one of the face atom and one corner atom. Okay, now let us do the calculation. We know that this is A and this is also A. So what is this distance from one corner to another corner? So it is nothing but, by using Pythagoras theorem, it is A square, okay, plus A square. Now, so this A square plus A square is the distance between this point and this point. So what is half of it? The half of it is by 2. Then this particular value is the distance between this point and this atom. So these two atoms, but we know that these atoms are bigger. Okay, and the atomic radius is going to be half of this value. I mean the atomic radius will be half of this value. So what will happen to the atomic radius? So the atomic radius will be root over of A square plus A square, okay, divided by half of this will be, so that is already 2, and the half of this will be give you a 4. So what is the answer? The answer is A by 2 root 2. A by 2 root 2. This is the atomic radius of the face centered cubic cell. I mean the atoms that are in the face centered cubic cell will have atomic radius A by 2 root 2, because there are atoms at the faces that occupy space. So this is much less. However, in the cubic cell, simple cubic cell, we saw that the atomic radius was just A by 2, because if you look at the simple cubic cell, the atoms only existed at the corners. You see, so if the atoms only exist at the corner, then there is no space taken by this face centered or body center. There's no space is taken, so the entire space is available to this corner, and hence the radius is bigger. But the radius of the atoms in the face centered cell is smaller. Okay, I hope you are getting this point. How about atomic radius in case of body centered? Okay, this is a body centered cubic cell. Okay, so what happens in a body centered is, you have this particular cube, okay, and you have these atoms at the corners, and you have one particular atom at the center. So please see, the atoms are bigger, so this will be a big atom at the center, and this will be a big atom at the corner. So the atomic radius can be calculated by, find the two nearest neighboring atoms, find the distance between two nearest neighboring atoms. You see, in this case, The distance between two nearest neighboring atoms are the body centered atom, that's center, the atom at the center, and the side. Okay, so what we need to do is, okay, let me draw the diagram again. So you have a cube, you have atoms at the center, and you have atoms at the corner, and you have atom at the center. So what is the nearest neighboring atoms? The nearest neighboring atom in body center is this corner atom and this body atom. Okay, so to calculate the distance between them, I need to calculate the distance between this part to this part. And once I calculate this violet line, what I'll do is I'll just make half of it. So look at the yellow line, the blue line, and the violet line. So what are the values? Okay, this has a value a, and this will have a value, since this is a and this is a, so the value of yellow line will be root over of a square plus a square. So what will be this value? Root over of a square plus a square, you will get root 2a. So the value of the yellow line will be root 2a. Now what is the value of violet line? So it's very easy. So by using Pythagoras theorem, what you need to do is you square the distance of the yellow line and the blue line. So yellow line was root 2a, so you need to square the value of this. I'm just using simple Pythagoras theorem. Okay, so this is actually giving me the calculation of the violet line. So what is the violet line value? This value is root 3a. Okay, so what is root 3a? Root 3a is the distance between this part and this part. So what is the distance? So if I half it, if I make it by 2, then what will I get? I get the distance between this part and this part. So what is the distance between two nearest neighboring atoms in body center? It is value root 3a by 2. And we know that, so what is root 3a by 2? Root 3a by 2 was the distance between this point and this point, the centers of these two atoms. So this is root 3a by 2. If I half it, what do I get? Of course I get the atomic radius. So what is the atomic radius in case of body center? It is root 3a by 4. This is the atomic radius. So you see, when we are calculating atomic radius, we are actually calculating the atomic radius. And as I said, don't be fooled by this diagram. The atoms are bigger here. The atoms are not that smaller that you think. The atoms are bigger, they acquire space, and when you are calculating the distance between two particular atoms and doing the half, we are actually getting the atomic radius. The atomic radius. Agreed? So once the atomic radius is calculated, now we'll move on to find something called as number of atoms per unit cell. Okay, let us discuss that. So number of atoms per unit cell. Okay, so this will be the part 2. In part 1 we discussed about atomic radius. In part 2 we'll discuss about number of atoms per unit cell. Now can you tell me how many cubes share this particular atom? We discussed earlier that this atom is shared by 8 cubes. So what is the contribution of this particular, or how much part of this particular atom is inside this cell? It's 1/8. Okay, so each atom has only 1/8 of its body inside the cell. So every atom has only 1/8 of its body. So only 1/8 of the body of each atom is contributing towards the cell. Now can you tell me what will be the total contribution? There are 8 atoms and each atom is contributing only 1/8 of its body. So how much am I getting? I get 1 atom per unit cell. So this is a hypothetical number that says how many atoms are actually contributing to the unit cell. Here you see each atom is contributing only 1/8. So total atoms are 8. So what is the total number of atoms that is actually contributing to the cell, it is actually 1. Having these 8 atoms is same as having this 1 atom. Okay, this is the meaning. Number of atoms per unit cell means if I have these 8 atoms, it is useless because all these 8 atoms are shared by many other cubes and each atom is giving me only 1/8 of its body. So having these 8 atoms is same as having the 1 atom with me. So number of atoms per unit cell in case of simple cubic is 8. Okay, what about the face centered? Okay, face centered is a very interesting application. So let me draw. So this is a face centered. What happens in a face centered? We have atoms at the corners and we have atoms at the center. Okay, now let us focus on the atoms at the center. You see this particular atom at the center, there can be only one cube on this side. So this face atom is actually shared by two cubes, cube 1, cube 2. So what is the contribution of this face atom? The contribution is actually half. If you have another atom here, this is also at the face, so at max you can have a cube at the top. Okay, if you have a cube at the top, can you tell me this atom is contributing how much to this cube? It is again contributing half. So all the face atoms, so all the atoms that are on the faces, the contribution is equal to half. And how many atoms do we have? We have on total of 6 atoms. Agreed? So having all these 6 face atoms is equivalent to having only 3 atoms, because each of the face atom is shared by 2 cubes. Not only we have this face atoms, we also have this atoms at the corner. So how much they are contributing? 1/8 into 8. So their contribution is 1. Okay, so having these 8, so per unit cell of face centered, having 8 atoms at the corner is equivalent to having 1 atom, and having 6 face atoms on the faces is equivalent to having only 3 atom. So what is the total number of atoms per unit cell for a face centered? It is 4. So for simple cubic it was 8, for face centered number, oh so sorry, this number will be 1, and for face centered we have 4. So can you guess what will happen to the body centered? What will be the answer for the body centered? For the body centered, the number of atoms per unit cell will be 2. Why 2? See, in the body center what happens? There is an atom at the center, and this atom is not shared by any other cube. So this atom is completely for this particular cube. So we have 8 corner atoms whose total contribution is 1, and we have 1 atom at the center whose contribution is 1 because it is not shared by any other cube. So what is the total value? 2. So for a body centered, the number of atoms per unit cell is 2. Okay, so what are we actually doing? So it is saying that this 2 number, the number 2 is saying that although the body centered has total 8 plus 1 9 atoms, but it is equivalent to having 2 atoms because the other 8 atoms are not sharing their entire body with this cube. They are only sharing 1/8 of the atom. So this is the meaning of number of atoms per unit cell. So we learned about atomic radius and we learned about number of atoms per unit cell. Now we will learn about packing fraction. Okay, and then I will tell you why we read atomic radius, why we read number of atoms per unit cell, and why we are reading packing fraction. Now remember one thing, the atomic radius and the number of atoms per unit cell, these two things that you have studied will help you in calculating the packing fraction. After defining the packing fraction, you will understand what are we doing. Okay, so what is packing fraction? So packing fraction is the ratio of total volume occupied by the atoms in unit cell and the total volume of cell.